Hello everyone. So in the last video, we looked at some things the first derivative tells us about the function f, but in this video, we're going to look at what the second derivative tells us about f. And the key idea here is going to be concavity. So what does concavity, concave up and concave down mean? So there, at the start, we're going to have this kind of geometric definition, but then there are going to be some ways of figuring out later with second order derivatives. Anyway, so if the graph of f lies above the tangent lines on an interval, we say that f is concave up. And if the graph of f lies below its tangent lines on an interval, then f is concave down. Okay, so on a picture, the pictures are something like this. So here on the first graph, this function is getting steeper and steeper. And wherever we draw the tangent line is going to lie always below the graph. Whereas on the second one, the curve is getting less and less steep. And wherever we draw the tangent line will lie above the function. Okay, so these functions are both increasing functions, and you can imagine they have the same endpoint, right? The endpoints are roughly the same, but the shape is very different. The first one is getting steeper and steeper, and the tangent lines lie below the graph. The second one is getting less and less steep, the tangent lines lie above the graph. So even though a function is increasing, it can have quite a different shape. Okay, so as it's written, it seems kind of confusing. How would we ever figure out if it's concave up or concave down unless we have the picture? Luckily, we can tell this with this thing called the concavity test, which is based on the second derivative. So if we have a nice function and we can differentiate it twice, if the second derivative is positive, then the graph is concave up. If the second derivative is negative, then it's concave down. So if they give you a picture, then maybe you can figure it out. But otherwise, if they give you a formula and you're asked to find whether the graph is concave up or concave down, you should go for the second derivative. Okay. And equivalently, as we kind of hinted at, concave up means that here we're saying the second derivative is positive. And remember, the second derivative is the derivative of f prime. So if the second derivative is positive, that means that f prime is increasing. Or in other words, the graph of f is getting steeper. And it's concave down when the second derivative is negative, which means the first derivative is decreasing, which means the graph of f is getting less steep or more steep negative. Okay. So here it's a simple example. So f of x is x squared. Okay, the second derivative is 2. All right, we differentiate once, we get 2x. We differentiate again, we get 2, which is positive. So that's always concave up, and which makes sense if you remember the picture of x squared. And then if we have square root of x, that's concave down, because when we differentiate twice, we get this function, which is negative. And that makes sense also if you think of the graph of square root of x. Okay, so next what we have inflection points. So a point is called an inflection point if f is continuous there and the graph changes from being concave up to concave down. So it's not just where the second derivative is 0, but it's where the concavity changes. So the second derivative has to change sign. So let's do an example putting this together. So let's find the intervals of concavity and some inflection points for this function. So x cubed minus 3x squared minus 9x plus 4. So what are we trying to do? Well, we're trying to work out the second derivative, and then we have to figure out the sign of the second derivative. If the second derivative is positive, it's going to be concave up. If the second derivative is negative, it's going to be concave down. And if the second derivative changes in sign, then it's going to be an inflection point. So let's put that into practice. So we differentiate once, we get 3x squared minus 6x minus 9. We differentiate again, we get 6x minus 6, which we can factor as 6 times x minus 1. So the second derivative is 0 at 1, and it's going to be positive if x is bigger than 1, and it's going to be negative if x is less than 1. Okay, so if x is bigger than 1, if we're in the interval 1 to infinity, then the second derivative is positive, which means the graph is concave up. And then to the left of 1, f double prime is negative, which means the graph is concave down. So this is the graph of f is concave up and down. And finally, the graph of f changes from concave up to concave down at 1, so that's an inflection point. So here are the things we just highlighted, we just introduced, right? Concave up, concave down inflection points. If we're given a function, we can figure them out with second derivatives. Okay, so now let's look at another test for figuring out local max and local min. So we had in the last video that thing called the first derivative test, which is looking at when the sign of f prime changes. So this is just another test. I mean, sometimes one is easier to use, sometimes the other is easier to use. So what does it say? Suppose we have a critical point. So suppose the first derivative is 0. And suppose the second derivative is positive, then f has a local min. And then vice versa, if the first derivative is 0, so if we have a critical point, and the second derivative is negative, then there is a local max. Okay, so please don't get confused on which order this goes. So the second derivative is positive means that there is a local min, and the second derivative is negative means that there's a local max. So it's easy to get confused. You think, bigger than 0, that means things are large, and then you might be tempted to write local max. If you do that, you'll get the wrong answer. So please be careful. with that one. So why? I mean, if you think about the second derivative is being bigger than 0, that means the graph is getting steeper and steeper. It's a little bit like x squared. If you think of the graph of x squared, it has a local min at 0. Or if you want to think of the second derivative being less than 0, it's the opposite, minus x squared. Okay, so let's look at an example. So let's try to find the local min and the local max of this function using the second derivative test. So we could do it with the first derivative test, but just to see how the second derivative test works, let's do that. So we have to figure out first why the first derivative is 0. Okay, if the first derivative is not 0, then nothing interesting is happening. So if we differentiate, we get 4x cubed minus 16x, and we can factor out a 4x. We get 4x times x squared minus 4. And now we're looking for where this is 0. So this is 0 either when 4x equals 0, or in other words, x equals 0, or when x squared minus 4 equals 0. So x squared equals 4, x is plus or minus 2. Okay, so our zeros are at 0, 2, and minus 2. So these are our critical points. And right now, we don't know if they're local max or local min or neither. So let's go on and use the second derivative test. If we work out the second derivative, going back to our formula for f prime is 4x cubed minus 16x, we get 12x squared minus 16 for the second derivative. Okay, and now we want to go ahead and plug these points in and see what we get for f double prime. Okay, so if we plug in x equals 2 or x equals minus 2 into our formula for f double prime, if you trust me, it will come out to 32, which is positive. And then we have to remember that, okay, if the second derivative is positive, that means we have a local min. Okay, so we have a local min at x equals minus 2 and x equals plus 2. Okay, and there you could find out what is the local min and the local max value. So it happens, the local min happens at x equals 2 and x equals minus 2. The value of f at those points we get just by plugging in those points into the original formula for f. That's going to be minus 16. So we have this local min of minus 16. Okay, and then we go back and we do our x equals 0 case. So if we plug 0 into the formula for the second derivative, we get minus 16, which is negative. Okay, and if the second derivative is negative, we remember that means there is a local max. Okay, so there is a local max at x equals 0. And we can go ahead and find the value of f at that point just by plugging in. We get f of 0 equals 0. So there is a local max at x equals 0, and the value is 0. Okay, so that wraps it up for this video. So remember the key points were the definition of concavity and ways to find concavity. If the second derivative is positive, that means it's concave up. If the second derivative is negative, it's concave down. If concavity changes, that's an inflection point. And then we had the second derivative test, which was a way of figuring out which critical points are local max or local min. And we had to be very careful, right? If the second derivative is positive, it's a local min. If the second derivative is negative, it's a local max. Okay, thanks everyone. Take care. See you next time.